Hi everyone, welcome back to the video on the control systems. Upon completion of the tutorials questions regarding the Lag Compensator design, you are usually wondering whether your solutions is correct or not. So in this video, I'm going to teach in a very simple way how do we actually verify our solutions using a standard tool such as the root locus and the step response. Let's look at the typical questions on Lag Compensator design, where you are required to design a Lag Compensator to place the poles at this location and a static velocity error constant of 50. To verify your solutions, we'll be needing the root locus to verify that the locations is correct, and then the static velocity error constant, we will need to use the RAM response. However, Matlab does not have a pre-built-in RAM response function, and hence we'll be using the step response with a minor tweaking to actually generate the RAM response so that the steady state error can be captured to verify the steady state error requirement. So now let's look at the Matlab coding. So we'll be going through the codes here in a step-by-step manner. First of all, this is the transfer function G as per the questions. We have 3 poles, one at the origin, -2 and -5 with a gain of 1, and this will be the transfer functions. And next, so this is what we designed. So this is our Lag Compensator. So this is our Lag Compensator with this value. So first of all, we need to verify whether our Lag Compensator is being designed correctly, so that the closed loop poles can be placed at the desired locations. So what we need to do now is to actually generate the root locus as such. So the root locus will be the root locus of the Lag Compensator systems with the Lag Compensator multiplied by the transfer function G. So in this example, we will omit the Lag Compensator because the Lag Compensator is designed in such a way that the locations of the zeros and the poles are chosen to minimize the effect on the shape of the root locus of the Lag Compensator systems. Hence, in our verifications, our main objective is to verify our Lag Compensator is being designed correctly. Alright, so this is the root locus after generating this command. So what we need to do is to click on any points of the root locus, and if the Lag Compensator is being designed correctly, so what we are going to expect here is that we'll be able to find the root locus to hit exactly at the locations that is being desired at the gain of 1. So at now, this is the best that I can move my cursor so that to hit the gain of very near to 1. So in this case, you can see that the pole value here is being achieved. So it's very close to -2 plus minus j2 square root of 3, and this will be able to verify that our Lag Compensator is being designed correctly. Alright, so next we move on to the Lag Compensator. So the Lag Compensator part, we have designed it to be at this transfer functions s plus 0.002 divided by s plus 0.001344. And what we need to do now is to actually generate the RAM response, but however, as I mentioned earlier, there's no RAM function in the Matlab. So what we need to do now is to cheat a little bit on this step response so that it can emulate out the RAM response. So what we need to do now is that instead of we actually just type the step response of the feedback transfer function with the lead and lag, what we need to do now is to additionally add an integrator 1/s into the system so that the step response can be integrated to form a RAM response. So the RAM response will actually go through the feedback systems, and here I specify the end time. So this part is the end time of the simulation, and I set it to be large enough so that we can capture the steady state response. So what this command will do here is that you will generate the RAM response until the 10,000 second, and you store the output value into these two variables. The first one, Y, denotes the output signals, and the T will be the time signal, and then the steady state error okay, the steady state error will be the difference between the output and the time. So this will be our steady state error, okay, and then this is our input, and input basically will be the same as the time because we are using the unit ramp, while this part will be our output. So the steady state error will be actually the output minus input when time approaches infinity. So therefore we will be getting the very last value of the output minus with the very last value of the time signal, and we will get 0.02, which is actually the 1/kV. So remember the steady state error is 1/kV and the requirement is 50 for the kV, and hence our 0.02 is actually verifying our solutions for the lag compensator. Alright, so that's all that I want to share in this video. Thank you very much for watching. Bye.